Episode 19, titled Probability Essentials, Events, Conditional Probability, and Independence, the goal is to build probability intuition that powers many exam questions, especially the ones that look simple but hide subtle wording.
Probability shows up everywhere in DataX, from interpreting risks and thresholds to understanding classification behavior and evaluating uncertainty.
The exam rarely asks you to be a human calculator, but it frequently asks you to reason correctly about given information, base rates, and whether events influence each other.
When you have solid intuition, those questions stop feeling like traps and start feeling like structured logic puzzles you can solve calmly.
This episode will keep probability grounded in meaning, not just formulas, because the meaning is what keeps you from mixing up similar concepts under pressure.
We will focus on events, conditional probability, and independence, because those three ideas form the core of most practical probability reasoning in data scenarios.
If you can interpret them correctly and apply a few basic rules, you will gain a reliable advantage across many question types.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A clean starting point is to define events as sets of outcomes rather than as single numbers, because that language shift prevents a lot of confusion. An event is something like a transaction is fraudulent, a customer churns, or a device fails, and each of those events includes many possible underlying outcomes that satisfy the description. When you think of an event as a set, you naturally understand that probability is measuring the likelihood that the actual outcome falls into that set, not the likelihood of one specific labeled number.
This matters because many exam questions talk about combinations of events, such as two conditions happening together, or one condition happening or another, and set thinking makes those combinations intuitive. It also matters because event can include ranges, categories, and conditions, which are often how real metrics are defined.
In operational settings, you rarely care about a single exact value. You care about whether a condition is true, which is exactly what an event represents. DataX rewards this set-based understanding because it makes conditional and joint reasoning far less error-prone.
Conditional probability is the next foundation, and the simplest way to describe it is modeling what you believe given evidence.
Conditional probability answers a question like, what is the probability of event A given that event B has occurred, meaning your uncertainty about A after you learn B?
This is the formal version of updating your belief when new information arrives, which is exactly how risk assessment and detection systems behave.
The exam often uses the word given, and that word is not decorative. It signals that you are conditioning on some information and therefore changing the probability.
For example, the probability of fraud given an unusual location is different from the base probability of fraud because the evidence changes your expectation.
Conditional reasoning is also how you interpret model outputs, where the model is effectively estimating the likelihood of an outcome given features.
When you treat given as a signal that you must update the world you are reasoning about, many probability questions become straightforward. Independence is a specific claim about conditional probability, and it means that learning one event does not change the probability of the other.
Two events are independent if the probability of A given B is the same as the probability of A without B, meaning B provides no information about A.
Another equivalent idea is that the probability of B given A is the same as the probability of B without A, which emphasizes that independence is symmetric in this informational sense. In real data settings, True independence is less common than people assume, because many operational variables are linked by shared causes, shared processes, and selection effects. The exam often tests whether you can recognize when independence is a reasonable assumption and when it is not. If you see a scenario where one event plausibly changes the likelihood of another, you should treat the events as dependent unless the prompt explicitly supports independence. DataX rewards this because independence is often the hidden assumption behind multiplication shortcuts, and using those shortcuts incorrectly produces wrong answers quickly. Recognizing dependent events in operational scenarios is one of the most practical skills you can develop because dependency is often implied by workflow, causality, or shared context. If a system is under load, error rates and latency are likely dependent because they are driven by the same underlying condition. If a customer has already exhibited certain behaviors, churn probability may depend on that evidence, meaning the events are not independent in a decision sense. If a device reports one fault, the probability of additional faults may increase because it signals degradation, which again creates dependency. The exam may describe sequences, triggers, or shared environment changes, and those descriptions are often dependency cues. Even when the question does not ask, "Are these independent?" the correct calculation or interpretation often depends on that decision. DataX rewards learners who notice that the real world is linked and who do not assume independence just because it makes the math easier. When you practice spotting dependency, you reduce the chance of being tricked by a problem that quietly relies on conditional thinking. When independence does hold, the multiplication rule becomes a powerful and safe way to compute joint probabilities. The joint probability of A and B, meaning both happen, can be computed as the probability of A times the probability of B if A and B are independent. More generally, the probability of A and B is the probability of A times the probability of B given A, which is always true and becomes the simple product only under independence. The exam often presents questions that involve "and" language, such as two conditions both being true, and the correct approach depends on whether the conditions are independent or whether one changes the likelihood of the other. If the scenario supports independence, multiplication gives you the joint probability quickly without overthinking. If the scenario implies dependence, you must use the conditional form because that is the correct expression of "and" when evidence affects likelihood. DataX rewards knowing the difference because it demonstrates you understand what independence buys you and what it does not. The addition rule handles unions, meaning A or B, and it becomes especially important when possibilities overlap. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B, because the overlap would otherwise be counted twice. In plain terms, you add the two event probabilities, but you must subtract the intersection because those cases were included in both counts. The exam may use wording like either, or at least one, and the correct interpretation depends on whether the events can both happen. If the events are mutually exclusive, meaning they cannot both occur, the overlap is zero and the union is just the sum, which is a common special case. If the events can overlap, you must account for the intersection, or you will overestimate the probability. DataX rewards this because many learners default to simple addition without checking overlap, and that produces incorrect results in realistic scenarios where events are not exclusive. Complements are a strong tool for simplifying calculations under pressure because they often turn complicated unions into a single subtraction. The complement of an event A is not A
meaning all outcomes where A does not occur. And the probability of A is 1 minus the probability of not A. This becomes especially useful when you are asked about at least one of something occurring, where it is often easier to calculate the probability that none occur and then subtract from 1. For example, if you are dealing with repeated independent trials, computing no successes can be easier than computing one or more successes directly. The exam often rewards this shortcut because it shows you can restructure a problem rather than getting stuck in complicated enumeration. Complements also help you keep your reasoning clean because they force you to define the event precisely and then consider its opposite. When you use complements correctly, you reduce the chance of missing an overlap case or double counting scenarios. Base rates act as prior probabilities in many decision problems, and the exam expects you to respect them because ignoring base rates leads to overconfident and often wrong conclusions. A base rate is the overall frequency of an event in the population before you consider specific evidence, such as the overall fraud rate or the overall failure rate. When you receive evidence, your probability becomes a conditional probability. But the base rate still influences the result, because rare events remain rare, even when evidence increases risk. The exam may describe rare positives and then provide a signal that seems strong, and the correct reasoning often involves recognizing that the probability may increase but may still be relatively low because the starting rate is small. This is not about doing full Bayesian computation unless the question demands it, but about not losing sight of prevalence. In classification contexts, base rates also influence precision because the proportion of positives affects how many predicted positives are true. DataX rewards this base rate awareness because it aligns with real-world risk reasoning, where priors matter and flashy signals can mislead. A classic trap is confusing mutually exclusive with independent, and the exam expects you to know they are different ideas. Mutually exclusive events cannot happen at the same time, like the same transaction is both approved and declined, and if two events are mutually exclusive and both have non-zero probability, they cannot be independent. Independence means learning one event does not change the probability of the other, while mutual exclusivity means one event guarantees the other does not occur. If A and B are mutually exclusive, then the probability of A and B together is 0, which changes the conditional probabilities in a way that violates independence unless one event is impossible. The exam may present language like either this or that and tempt you to assume independence, or it may present independence language and tempt you to assume exclusivity, and the correct answer requires keeping the concepts separate. When you see cannot both happen, think mutual exclusivity and union without overlap, and when you see does not change likelihood, think independence and multiplication shortcuts. DataX rewards this distinction because it prevents a common error that cascades into wrong calculations. Probability thinking links directly to classification, risk, and thresholds, because classification decisions are essentially probability decisions disguised as labels. A model score often represents the estimated probability of an outcome given features, and a threshold turns that probability into an action. Changing the threshold changes the balance of false positives and false negatives, which is a probability-driven policy choice. Risk decisions also involve conditional probability, because you are often estimating the probability of a bad outcome given evidence and deciding what action is justified. The exam uses this connection by presenting scenarios where you must interpret what a score means, how base rates influence outcomes, and how given information changes risk.
When you understand conditional probability and independence, you can reason about why precision changes with prevalence and why calibration matters when probabilities drive decisions. DataX rewards the learner who can connect foundational probability to operational evaluation because it shows you understand the meaning behind the metrics. This is also why careful wording matters, because small language shifts can change the conditioning and therefore the correct interpretation. Because wording matters so much, you must handle given language carefully, since it signals conditioning and therefore changes what probability you are computing. The probability of A given B is not the same as the probability of B given A, and many exam distractors rely on swapping these by accident. When you hear given, your first step should be to identify what is being conditioned on, which is the evidence you are assuming to be true. Then identify what you are trying to predict, which is the outcome whose probability is being asked. This habit keeps you from mixing up direction, and it also keeps you from using the wrong base rate, because conditioning changes the reference group you are considering. The exam often frames this with realistic language rather than symbols, which is why translating the sentence into probability of outcome given evidence is so helpful. When you do this consistently, probability questions become a structured reading challenge rather than a math surprise. DataX rewards this careful conditioning habit because it is how professionals avoid subtle reasoning errors in risk assessment.
A strong memory anchor is that given changes the world, and independence says it does not, because it captures the heart of conditional reasoning.
If you learn something, your probability should usually change, because information changes expectation, and that is what conditional probability formalizes. Independence is the special case where learning the other event provides no information, meaning the probability does not change, and that special case is what allows simple multiplication.
Under exam pressure, this anchor helps you decide whether you should treat events as dependent and use conditional forms, or treat them as independent and use shortcuts.
It also helps you interpret scenarios where evidence is presented, because you can ask whether that evidence should change your belief about the outcome.
If it should, you are in conditional territory, and if it should not, independence may be plausible.
DataX rewards this anchor-driven reasoning because it keeps you consistent and reduces the chance of being tricked by a single word.
To conclude Episode 19, solve one verbal probability case by speaking each step, because that practice forces you to respect events, conditioning, and independence without getting lost in symbols. Start by naming the events in plain language as sets of outcomes. Then identify whether the question is asking for a joint probability, a union probability, or a conditional probability. If the question includes given, restate it explicitly as probability of outcome given evidence, and then decide whether independence is assumed or contradicted by the scenario. Use multiplication for and only when independence holds or when you correctly apply the conditional form, and use addition for or while accounting for overlap unless the events are mutually exclusive. When possible, use complements to simplify at least one statements, and always keep base rates in view so you do not overreact to evidence. If you can narrate that flow smoothly, you will handle probability questions across DataX with calm, accurate reasoning and consistent exam-ready judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.